Good morning, my name is Alejandro Mejia, and I'm going to present you the assessment of the PLC code generated with the GEMMA-GRAFCET methodology. I'm going to divide the content of the presentation into 5 principal points. I'm going to start with a brief introduction about the topic. Then I'm going to present you the research question and the objective. Next, I'm going to show you the workflow applied into the project. And then I'm going to introduce the results and analysis, and at the end I'm going to close with the conclusions and the future work. So to start talking about this project, it's important to introduce the Industry 4.0. This industry was created as an industrial revolution with the purpose of transform the traditional manufacturing into digitalized, interconnect, and interpreted system, for example, as the cyber-physical systems. These cyber-physical systems have some important characteristics as first, it allows the massive personalization that required the industry nowadays. Second, these systems are monitored, coordinated, and integrated from the same nucleus. In the most of the case, the nucleus are in the cybernetic space. And third, the system have vertical and horizontal communication. The vertical communication refers to the interaction between the cyber world and the physical world. Meanwhile, the horizontal communication refers to the interaction between systems of the same production line. So these two types of communication creates the necessity of the interoperability, understood as the ability to exchange information and knowledge. This way, the interoperability is based in two facts. The first one is the industrial Internet of Things that refers to all the ways that the systems are interconnected. And the second one is the use of syntax and semantics standard. This is for the correct interpretation of the transmitted data between systems. So this create a huge challenge due to the lack of universal standards. But the GEMMA-GRAFCET methodology was proposed to help and improve this challenge. The GEMMA-GRAFCET methodology is a way to create code and is based into important things. The first one is the GEMMA guide. It's a guide created in French to define the start, stop, and emergency modes of production systems. However, the GEMMA guide have a partial syntax and semantic specification that could end in possible emergent behaviors. So the GEMMA-GRAFCET methodology proposed to join with the graphic representation. And in other words, there are two-layer specification software that is composed by the operational modes represented with the GEMMA guide, and each operational modes contains a nested behavior represented in function block. This through a hierarchical design pattern could give the software specification of cyber-physical systems, and at the end a translation into code. One example of cyber-physical systems are the PLC. So at the end we are going to obtain PLC code. However, this GEMMA-GRAFCET methodology has not been evaluated regards the interoperability. But before entering this evaluation problem, we have to establish a point of reference. So we propose the state chart based methodology for create code. This is a planar representation of a system. It is only composed by states. A difference between this and the GEMMA-GRAFCET, where are two layers, two hierarchical layers. So the state chart based methodology requires a design pattern, not a hierarchical design pattern, to obtain the PLC code. With these two methodologies and the point of reference defined, we can propose a research question. That is, how effective is the GEMMA-GRAFCET for improve the interoperability? And to try to answer this question, we propose the following objective. As general objective is assess the PLC code generated by the GEMMA-GRAFCET methodology. And as specific, we propose build a virtual model of the hydroponic system. This is because we need a system to try the both codes. Second, apply the GEMMA-GRAFCET methodology to control the proposed model. So when we have the system, we need now the control part. Third, validate the PLC code through a virtual commissional simulation. So as the system is built and the control is built, we need to validate the code with the simulation. And fourth, compare the performance of the GEMMA-GRAFCET and state-chart methodologies to write PLC code. So when we have a correct simulation and validation, we have to compare that results. So with this objective defined, we can plan a workflow to develop this project. So we propose 4 stages. The first one is the case study, then the PLC code part, next the software metrics, and at the end we have the comparison. I'm going to explain each one later, but we can enter now in the results parts. So as first result, we have a case of study. We need this to have a system to try the code. And with the definition of the case of study, we have to identify the functional requirements of the system. So we select a wheel soilless flexible test bench related with hydroponics. It is composed by two modules. The first one is the nutrient solution generation module that takes tap water, then filter, and then combine with nutrients to irrigate plants. And we have the fertigation module that receives the prepared solution of the other module and make the distribution process between two lines of plants. So we have a video here. We can see the system represent in an HMI. So the operator enter 4 parameters that corresponds to the electrical conductivity and the pH objective of each line. These parameters are going to be modifying the tap water with the help of the nutrients, and these are specifically corresponding to the plants. So when the tap water is obtained and then filtered in this tank, the 240, they are connected to the nutrients. And when the system ends mixing this solution, pass to the second module, and it knows to which line corresponds the prepared solution. So when it's ready, it repeats the process with the second line. And when there is triggered the irrigation process, the system enter until the threshold is near. So when we have ready the case study, we can pass to the stage of PLC code that correspond to the part of write the code with both methodologies, and to the virtual simulation, virtual commissioning simulation, to check that the functional requirements are fulfilled. So in the PLC code planning process, we have basic software architecture. The both codes are going to be write in codices, and the principal task is going to be divided into 3 principal POUs. The first 2 are correspond to the control of the two lines, and the third one correspond to the actuations of the elements of the system. So we have we have here the representation of the GEMMA-GRAFCET methodology, the part of the operational modes. This was made with an automatic code generator, only for the operational modes. And here we have the representation of the nested behavior. In this case, it's in a state chart, but is similar to the graphic representation. Here we have the state chart based methodology for the system. It's composed by 3 macro states and 5 states and some substates that represent the same working principle with the GEMMA-GRAFCET. So when we have the PLC code ready, we have to make the mathematical model we made in Simulink, and it's composed by subsystems with some parameters. So the elements are represented in subsystems, and then are connected to obtain a complete kinematical model of the system. In this case, we have illustrated only the part of the nutrient solution model. So when we have all the process of the simulation and the mathematical model and the PLC code, we have to establish which metrics we are going to use. So we establish some components. We establish 4 components: complexity, reactivity, modularity, and maintenance, and divide into 2 types of analysis: statics and dynamics. The complexity is going to be evaluated through McCabe and Halstead. McCabe evaluate the part of the ways the code could have. Meanwhile, Halstead evaluate the structure, and both correspond to a static analysis. In the part of reactivity, we have response time and execution time. Both correspond to dynamic analysis. The response type is related with how much time have or need the code to repeat some steps, some defined steps. And the execution time refers to how much time required each code to run the POUs. The modularity is going to be evaluated through Kafura static analysis. This is going to be analysis of data exchange between POs and the fragmentation and the modularity. The 4th component is the maintenance, that is going to be evaluated through the maintenance index. This is a static analysis, and is going to tell how maintainable is a code. Maintainable related with how easy is to add a new function or to find an error. So when we have defined the metrics, we have to establish how we are going to measure or to calculate. So for the static analysis, we have 2 ways. The first one is the source code analysis, and the second one, the cohesive static analysis. There is a tool in cohesive that are going to help. The first way is to calculate manual. In this case, we use with Kafura and maintenance index. And for the cyclomatic complexity or McCabe and Halstead, we use the cohesive static analysis that automatically calculate these values. For the dynamic part, we use only cohesive test manager to calculate both metrics. For the response time, we establish some repeatable steps for both codes. For the execution time, we instrument the code. So we put timestamp at line 1, and that is the start, and at the end of actuation out stamp, and then we make the difference. So as we establish how we're going to make and the obtain of data, we can make the comparison now. And in this point, we are going to try to find advantage and disadvantage of each methodology. So for the static analysis, we obtain a spider plot. In the green area, we have all related with the stage chart methodology. In the orange, we have all the part of GEMMA-GRAFCET methodology. So if we analyze, we see that if cyclomatic complexity and the parameters are less, it implies a shorter and simple code. This corresponds with the result of the state chart and the values, because it have less states and nested, and as the state chart don't have nested behaviors and function blocks, it's going to be less lines and it's going to be shorter and simple. By other side, we have Kafura, that in the case of GEMMA-GRAFCET is a high value. This means that require more data exchange between the POs, and is represented in this value, in this metric. By other side, we have maintenance index that has a proportional increase respect to the maintenance of the code, so a greater value, more maintainable code, and the fragmentation that have GEMMA-GRAFCET allows to find easy an error or to add a new function. For the part of dynamic analysis, we can see that there is a difference, kind of 12 seconds, and in the response time, and it means that the GEMMA-GRAFCET methodology require to pass by more states, function blocks, and POs to do the same function that the state chart methodology. In the case of execution time, we take the worst case. There are no statistically significant difference, so it means that the POs are running in a similar time. And to close, I'm going to present the conclusions and the future work. So in conclusions, we have that the GEMMA-GRAFCET has a greater grade of maintainability related to the code fragmentation with a similar execution time of the state chart methodology. This is as the GEMMA-GRAFCET is more fragmented, is easily to find an error or to add a new function. So it's a more maintainable code. Second, the cyclic code fragmentation generated by the hierarchical design pattern results in a modular code. This is the result of half nested behaviors, the operational modes. Third, the GEMMA-GRAFCET methodology presents great complexity and response time due to the interconnection between POs. This is related with the that there is more data exchange between the function blocks and the POs. The fourth, the automatic code generation reduces the complexity problems. As we use the automatic code generation, require less effort from a programmer. And last, the applied research workflow has the potential to become an approach for the comparison of methodology for the development of PLC code. At the end, we find that is a very powerful guide or methodology to compare PLC code. So we identify as future work 3 things. The first one is apply the presented protocol for evaluate different proposed methodologies for PLC code generation. The second one is apply the comparison protocol with different test case scenarios. And the third one is implement the GEMMA-GRAFCET methodology in a physical system. Thank you.